All the fundamental components of our atomic structure had been discovered by the early 1930s. We haven't talked much about electron structure in this chapter. That's so central to modern chemistry that it actually gets its own chapter. But the basic model of an atom was like this. Protons and neutrons together make up a very small, dense nucleus at the center of an atom, and that dense nucleus is surrounded by electrons floating in what is mostly empty space. The research discussed in the next chapter, which largely occurred before neutrons were discovered, tells that electrons are in electron clouds that have mathematical definitions. Each of the subatomic particles has been characterized at this point, with protons and neutrons both having similar masses and electrons being several orders of magnitude less in mass. Similarly, the charge on protons and electrons was known to be equal and opposite, even as the signs are arbitrary. We briefly introduced the periodic table in the last chapter, but we can now see that the periodic table contains a lot of information that is directly related to the structure of an atom. In the top left of the entry shown is the atomic number, which corresponds to the number of protons in an atom, which never changes for that atom. Because atoms are neutral, this also corresponds to the number of electrons, but the number of electrons can change with charge. The atomic number is always a whole number because no known type of matter has partial protons. In the top right of the periodic table entry shown is the average atomic weight. This is an average over all known occurrences of the element on Earth. It's not exact because protons and neutrons don't mass exactly one atomic mass unit, but it's also not exact because many elements have multiple possible isotopes with different mass numbers. We'll talk about how these are calculated in just a moment. Also on the periodic table is the chemical symbol, which corresponds to the identity of the element. Every chemical symbol is tied to a specific atomic number, regardless of isotopes. So you can see there are two isotopes of beryllium shown, both having the same atomic number, even as the mass number of the particular isotope, which is indicated by the mass number on the top of the label, is changed. This form, with a mass number superscript and atomic number subscript, followed by the chemical symbol, is commonly used as a shorthand when specific isotopes need to be indicated. Most isotopes are referred to with this type of indicator only, a mass number on top, an atomic number below, and then the chemical symbol. But hydrogen isotopes also have special names and symbols that are widely accepted. A hydrogen isotope with a neutron and proton has an atomic mass of about 2 and is called deuterium. It has the symbol D. While a 2-neutron, 1-proton hydrogen with an atomic mass of around 3 is called tritium, indicated with the symbol T. Atomic weight is the weighted average of all the naturally occurring isotopes of an element. It is relatively easily calculated if the masses of independent isotopes are known and their abundances are known. We essentially just take every percent as a decimal value, meaning 99.274% is 0.99274, and then multiply it by the isotope mass, and then add them all up. The calculation looks like this for uranium. Notice that elements that are trace or synthetic, I didn't include the calculation, since their abundance is essentially 0. If you have a periodic table or the internet, you should be able to check your calculation fairly easily by searching for that specific element's listing. We got an average mass of uranium as 238.028. Look it up and see if it's right. You can also do the same calculation in Excel really quickly. Notice that I did have to change synthetic or trace to actual zeros to get the formula to calculate. You could also delete the rows for the same effect. If you know the actual average mass from the periodic table, or you can find it in a bulk sample, and you know the mass of all the relevant isotopes, you can actually go back and calculate the abundance for many species as well. This is useful in geology for radio dating. Different age minerals will have different ratios of isotopes. The math follows the same logic. The abundance all needs to add to 100%, or 1 as a decimal. So whatever the mass of one isotope is, here we set copper 63 as X, the mass of the other isotope should be 1 minus that. So we set copper 65 as 1 minus X. At this point, you can use the same formula as before, but already knowing the average mass. Each abundance is multiplied by the isotopic mass that goes with it, and you can commute it out, the 1 minus x. Combining the terms and solving for x is just an application of algebra, as is solving for 1 minus x. While it is convenient to be able to find abundance of a sample based on known values and an atomic mass, it's a fairly difficult set of measurements to make precisely enough to have meaning, especially for very old samples. We actually use a mass detector instead, in some ways similar to Thomson's cathode ray tube, in order to determine the mass-to-charge ratio of atoms in a sample and their relative abundance. It works like this. Sample is dissolved into a solution and dispersed as a fine cloud. A heater vaporizes the solvent to leave behind individual atoms, which are shot with an electron beam to ionize them. They lose electrons and become positively charged. The ions are accelerated toward negatively charged plates with a slit and deflected by a magnet. Lighter atoms are deflected more, and a calibrated detector can tell how many particles hit in different areas. The number of hits tells abundance, and the location on the detector tells what the mass-to-charge ratio is. Now that we've seen the electronic structure of atoms, it's easy to see that we need some sort of representation for atoms and molecules that isn't a drawing of the entire structure every time. If an atom is just on its own, we can, and do, use its elemental symbol to indicate it, sometimes with a circle to show the electron cloud, as shown, sometimes not. With that is implied all the atomic structure that comes along with it. The problem is, there are only a handful of atoms that exist on their own, and so we need some way of showing bonding between atoms. The simplest molecule, H2, can be shown with two hydrogen atoms' electrons clouds overlapping, but this starts to get complicated really quickly. If we try to do this for more complex organic molecules, even just showing lines between atoms without any labels can be really cumbersome. So, we use a wide variety of forms of varying complexity to describe molecules in different ways and in different situations. Working from the right, it's somewhat common to use a space-filling model to indicate the three-dimensional shape of a molecule. While atom labels aren't generally included in this form, most people use consistent color schemes for the atoms. Carbon is black here, and hydrogen is white, and the molecule shown is CH4, or methane. In this scheme, oxygen is typically displayed as red, nitrogen is blue, and sulfur yellow, even though none of those are used in this particular molecule. Again, this works really well for simple molecules, but it's really difficult to apply usefully for any large molecule. The ball and stick model, the next from the right, simplifies this a little bit because it shrinks down the atom size and displays the bonds. The atoms actually take up more space than is implied here, but it makes it much easier to see the details in the larger structures. Even so, this gets pretty complicated in most organic molecules, and so we have a variety of structural forms that show details quickly and accessibly, but often shortcut actual molecular shapes. The form least similar to the actual molecule is the molecular formula, shown all the way on the left. We do a lot with molecular formulas in general chemistry, but we'll quickly realize in organic chemistry there may be dozens of molecules with the same formula, all with different reactivity, and so we'll use structural formulas, lettered B here, to show those instead. From the structure of an atom, it's easy to arrive at the structure of an ion as well. This is covered more formally later, but I wanted to give a teaser here because it's so closely connected to the atomic structure and to the concept of molecular formulas. An ion is any atomic or molecular particle that is charged, and it becomes charged as electrons are gained or lost. Atoms that lose negatively charged electrons, like the beryllium ion shown, become positive. Positive ions are known as cations. It's easy to remember because cations are positive. Anions are negative ions, which come from gaining electrons. I remember anions are negative by thinking of anion as a short for a negative ion. Ions often exist together as compounds with balanced charge, which we indicate with a formula for the ionic compound that gives the lowest possible ratio of those compounds. So for beryllium chloride, as shown, we'd say that the formula unit is BeCl2. There are 2 chlorines for every beryllium to make a neutral charge. We don't put or say the 1 after beryllium, but if there are multiples, we'd always indicate it. The formula BeCl2 should imply that for every beryllium, there are 2 chlorides. It should distinctly not imply that there are packets of beryllium with exactly 2 chlorides floating around. These tend to exist as much larger lattices. Here's another example of an ionic compound, titanium dioxide, showing how it actually exists. Titanium dioxide, a white pigment background used in 2/3 of all pigments, has a formula of Ti for titanium, O2. But as you can clearly see in this structure, it's impossible to distinguish which titanium, which are gray here, go with which 2 oxygens. The formula unit we described for beryllium chloride can also be described as an empirical formula, a broader term that also encompasses non-ionic compounds. In both ionic and molecular cases, empirical formulas only give ratios of atoms, but absolutely do not give any sort of meaningful description of how many atoms are interacting or even how many are forming a unit. Again, the empirical formula also applies to molecules that aren't ionic. Empirical formulas are easier to find since we can often assess empirical formulas with relatively simple pieces of equipment. In many molecules, the empirical formula is not actually the molecular formula. The example shown above is acetic acid, the component of vinegar that makes it vinegary at only 5% concentration. The structure is shown as both a structural formula in B and as a ball and stick model in C. But the empirical formula would only show the simplest ratio of these atoms, which is Ch2O. If we didn't know this was an empirical formula, we think it is the only compound that exists with that molecular formula, formaldehyde, which has the same empirical formula but is much worse to consume. While an empirical formula should never be misinterpreted as a molecular formula, which of course requires good labeling practice, the molecular formula is always some multiple of the empirical formula. In formaldehyde, the molecular formula is the same as the empirical formula, that's that Ch2O. In acetic acid, the molecule shown, the molecular formula, is 2 times its empirical formula, C2H4O2. Even though molecular formulas are nice, concise ways of describing molecules, they have all sorts of problems with bigger molecules to the point where we don't really use it at all in organic chemistry. Molecular formulas don't tell us anything about actual structure. For example, the molecule shown on the left, ethanol, and the molecule shown on the right, dimethyl ether, actually have the exact same formula, even though they are completely different molecules. We call 2 molecules with the same formula but different connectivity between atoms structural isomers, which are one of many types of isomers, that is, molecules that are different from each other despite sharing the same formula. Another example of isomerism that is centrally important to medicine, protein, and carbohydrate chemistry can be seen here. These isomers of carbone are connected identically, but are pointed oppositely in space. They're mirror images, but you couldn't put them on top of each other to line them up. A good comparison is your hands. All the fingers of your hand are connected in the same way on your left hand and on the right hand, but they're pointed in the opposite direction from each other, and so they have different properties in some cases, like if you tried to wear a baseball glove on the wrong hand. This type of isomer is called a stereoisomer. Because many of your smell receptors are shaped in either right or left-hand versions, the right and left-hand version of this molecule smell and taste very different from each other, even though they're connected in the exact same way. Plus carbone, shown on the left, gives caraway its taste, while minus carbone is one of the dominant flavors of spearmint. This is even more important in later coursework. We'll find that in some cases, one stereoisomer of a molecule may be a useful pharmaceutical, while the other can give dangerous side effects. We often talk about molecular formulas, or even molecular structures, as if we could work with them in a very direct way. Unfortunately, we generally can't directly manipulate molecules, and it's pretty difficult to observe them directly as well, unless you're Paul Rudd, of course. That's because the scale of molecules is such that a hydrogen's atom mass is about 1/millionth of a millionth of a millionth of a millionth of a gram. For reference, a gram is about the mass of a paperclip. For this reason, we almost never count molecules, and instead, we indirectly look at the amounts of molecules based on mass. Just like we don't go to the store and buy eggs one at a time, we use a dozen to count out the eggs 12 at a time. The term dozen for 12 is widely understood and allows us to deal with units like eggs all together in a bigger group. We use the same strategy for atoms and molecules so we can actually get an amount that we can mass out. We start out with one atom of carbon-12, which weighs 12 atomic mass units, and to define a number in such a way that the grouping will give us a mass of 12 grams. So we have to have a number that gets us to 12 grams from 12 atomic mass units. That number is much, much bigger than a dozen, but it functions in the exact same way. Instead of a dozen carbons to get 12 carbons, we say that a mole of carbons gives us the equivalent mass in grams of carbon. This conversion is essential because it allows us to easily move between what is happening at the atomic scale and what we can actually measure on an actual scale. However, it's an experimentally defined number, so we can only know it to a certain amount of precision allowed by our experiments, which, as you can see, is actually not that bad. We've got a lot of precision for this number. I challenge you to measure anything to 9 significant figures. Notice, once again, that this is a very large number, almost a millions. By using this conversion, we can talk about molar mass of a mole of atoms. We give it the units of grams per mole, instead of talking about atomic mass in units of atomic mass units per atom or per molecule. So, which is the atomic weight on the periodic table? Turns out it's both. The relative masses of all atoms are consistent to each other, so a mole of a substance in grams weighs the same as a single atom or molecule in atomic mass units. That's great because now we can actually measure a mass and relate it back to what actually happens at the molecular level, but we never use mass directly. We're always going to need to use moles of a given substance so that our ratios will be the same as ratios of atoms. For this reason, whenever we're talking about any sort of chemical change that might occur, we always need to be talking in terms of mole. So converting into moles is one of our most important unit conversions. So how do we get from the grams that we can actually measure to the moles that we can actually use for chemistry? It's really a question of dimensional analysis. What do you need on the top and what do you need on the bottom to get from grams to moles? You need grams on the bottom to cancel out the initial unit and moles on the top to give the new unit. We don't actually have a conversion factor like that, but our molar masses from the periodic table are exactly the opposite, grams over mole. So this is just 1 over grams per mole, or 1 over molar mass. You can either think about this conversion from grams to moles as by multiplying by the inverse of molar mass, multiplying by 1 over molar mass, or just simply dividing by molar mass to get to moles, whatever is easiest for you to conceptualize. Let's think about this in terms of an actual problem. A problem I don't have, but a problem that someone probably does. If someone had a 1.000 kilogram bar of gold, how many moles of gold would they have? Of course, we'll need the molar mass from the periodic table, which is 196.966569 grams of gold per mole of gold. We probably want that many significant figures because it's pretty valuable. One of the first things I hope that you notice is that the units don't match up. We have a mass in kilograms, but a molar mass in grams. That's an easy fix. We can convert from kilograms of gold to grams of gold without a problem. It's exactly 1,000 grams, notice the decimal at the end of the number, which is a way of indicating that every digit before the decimal is significant. Now that we have grams, we can convert to moles using the same reasoning as before. We keep 1 with the moles of gold and put it on top and put 196.966569 grams of gold on the bottom, effectively dividing it by the molar mass. We get 5.077 moles of gold, 4 significant figures. For reference, this is about 3 times 10 to the 24th atoms of gold. If we split evenly between the approximately 7.8 billion people on Earth at the time of this recording, each person would have about 3.9 times 10 to the 14th atoms of gold, or 390 trillion atoms per person, which, at a price of about $56,000 per kilo, it would be worth a little less than 1/1000th of a cent. Going back the other way is easier. If we have a molar quantity and want to find grams, we can set it up as a dimensional analysis problem again. But the conversion factor we're looking for is grams per mole, which is molar mass. Mass times molar mass is moles. For fun, let's do a balloon calculation. It is actually fairly easy to find moles based on the volume of a balloon. We'll do that later, but if you've ever tried to take the mass of a helium balloon, it doesn't work so well. So if we know that we've filled a balloon of a given size, like one of those Mylar ones that doesn't stretch, with helium, we should be able to figure out what it weighs with science even if we can't do it with a scale. For reference, the molar mass of helium is 4.002602 grams helium per mole helium. Why don't you try to set up this problem first? What is your given and what is your target unit? And will you need to multiply or divide by molar mass to make the conversion units work out? Good. So the answer is 0.214 grams of helium. It's worth noting that most substances are not just elements, but some sort of compound. The molar mass of the entire molecule, the molecular mass, is just the sum of all of its components, and it can be used in the same way. I actually set this up in Excel, but I made it all fancy for PowerPoint. I could add 12.01, the atomic weight of carbon, to itself 6 times, and then repeat with hydrogen and oxygen. But it's easier to just multiply the number of carbons by the atomic weight of the carbon, and then repeat with hydrogen and with oxygen, and then add it all together. Adding all the components together gives me the molecular mass for this formula, 180.16 grams per mole of glucose. If we want to convert grams to moles, we again just use molecular weight as the conversion factor, the same as we did with a molar mass or an atomic mass. In this direction, we're going to need to divide to get the grams on bottom, and our result is 0.0158 moles of delightful pixie stick sugar.